So hey everyone, this is Mayur. Welcome back to MLWorks. In this video, we'll be understanding what is LoRa and how it is being used in deep learning for optimization. Okay, so let's understand LoRa first. LoRa stands for Low-Rank Adaptations, and it is a fine-tuning technique that reduces the number of trainable parameters. Okay, and how it happens is it tries to create a small number of new weights in the existing model. For example, if you have Llama 3 model, what you do is you add a small bunch of weight parameters, and during the fine tuning or the training process, you just keep updating that new weights. Okay, so what happens at the end is you will be training the model faster because you just have small number of weights, and the memory will be efficient because you just have small number of weights again. Okay, and you will be producing a smaller model, and which will be aligned along with your existing model, which is pre-trained model. Okay, and which will be easier to store and share. So why LoRa, right? So these techniques, why it came into picture. So consider you have models like GPT, Claude, Llama. Okay, these are like billions of parameters are present, and they are huge in size. Even the infrastructure that is required to load such a model is quite expensive. Okay, so it's quite difficult to host such a model. And you can also, there are techniques like one-shot prompting, where you can pass your feature plus target and give it to LLM, and it will be understanding the nuances of your feature and target. Okay, and it try to generate. But this is not possible for complex tasks like text to code or any specific use case related to finance or healthcare, right? Where you have to fine tune a model. You cannot just directly give one shot prompting. Okay, and there is something called as fine tuning of LLMs that can be done. But these fine tuning of LLMs, like for example GPT-3, which is 175 billion parameters, okay, these are super expensive to do, and the infrastructure that is required to do fine tuning of such model it's beyond, like only large corporation can do it actually. One cannot do it on their own. Okay, so yeah, that's when LoRa comes into picture, which is a fine tuning of large language models. So let's understand that. So how it works at high level. Okay, so at high level, what it does is it just creates, you have your original model, which is Llama 3 or GPT models, and you just add a small part or a small weight, okay, to each of the layers of your model, original model, and you just keep updating that small change rate, small layer or small weight, whatever you added, you just update that while during the fine tuning process or the training process. Okay, so what it will lead to is it will lead to less trainable parameters. You don't have to touch the whole original model. You just have to update the small new weights, and then it will automatically reduce the memory requirement of the GPU or the CPU wherever you are running it. And this will lead to faster training because since you have only small number of parameters to train on, and it is easy to cache because since the model will be small, you can cache the model also. So example, right? For example, okay, you have full fine tuning of GPT-3 model, which will require. So if you're doing a fine tuning job of a GPT-3 model, there are 175 billion parameters that needs to be updated. Okay, but if you use LoRa, what will happen is you will reduce the number of parameters by 10,000 times, and also the GPU requirement by 3 times. Okay, so that's the effect of LoRa when it comes to fine tuning. So let's understand the math behind LoRa, right? So LoRa is low rank adaptation. So this is a basic algebra, linear algebra concept. Okay, what is rank first of all? In a matrix, okay, rank in an abstract form refers to the information content or the dimension of the data inside the matrix. In this case, if you see, this is a 3x3 matrix. You have 1, 2, 3, 2, 4, 6, 3, 6, 9. So this is your information content of the matrix. Now, what is the rank represents, right? It is a number of independent rows or columns in a matrix. Okay, so you should understand this part, like very important, which is the number of independent rows and columns in the matrix. That's when you come into a position called as low rank matrix. So if you see here, a matrix is low rank if the rank is less than the maximum possible rank of the matrix. Okay, let's understand this part first. Let's understand the number of independent rows and columns in a matrix. So you have a matrix here, A, 1, 2, 3 is the first column, 2, 4, 6 is the second column, and 3, 6, 9 is the third column. And if you are reading it row wise, the first row is 1, 2, 3, then you have second row 2, 4, 6, and third row 3, 6, 9. Now, with the help of one column or with the help of one row, we are able to achieve other rows and columns. For example, okay, if you are taking in the first column, which is 1, 2, 3, okay, here I am showing it here, 1, 2, 3. If you multiply with 2, you will receive your second column, and if you are multiplying it with 3, you will receive your third column. So these two columns are not dependent. These are dependent on 1, 2, 3. This column is dependent on this one, and this column is dependent on this one. Similarly, okay, if you have row 1, 2, 3, okay, first row, again, if you multiply it with 2, okay, you will receive row 2, and if you are multiplying it row 3, multiply it with 3, you will receive the row 3. So the only one independent column is present, which is 1, 2, 3. Either you can take it row wise or column wise. Okay, there is only one possible independent row or column. Okay, so out of 3 cross 3 matrix, okay, only one is independent. Okay, so the rank of the matrix is 1, but the maximum possible rank is 3. But in this case, since the two rows or two columns are dependent on one row or one column, so we are turning the rank, maximum possible rank, from 3 to 1. So as mentioned here, the maximum possible rank is 3 because the matrix is 3 cross 3, but only one independent row is or column is present, which is 1, 2, 3 or row wise or 1, 2, 3 column wise. So hence the rank is 1. So any matrix, okay, which can be reduced like this, okay, is a low rank matrix. So a matrix is low rank if the rank is less than the maximum possible rank. Okay, so in this case, the maximum possible rank was 3 and we were able to reduce it to 1. So this matrix is low rank matrix. Now low rank matrix, right, it is helps in data compression since we reduced it from 3 to 1. Okay, that's why it is what data compression is used for data compression, and it is following something called as Rank-nullity theorem, and which is stated here, where the theorem states that the dimension of the row space, that is space spanned by the rows, okay, which are the rows which I mentioned, right, 1, 2, 3, and the column which is again 1, 2, 3 are equal. Okay, this common dimension is what we refer to as the rank of the matrix. Now let's understand how LoRa uses low rank matrices. Okay, so in the traditional fine tuning, what we do is you will have your weights, okay, all the trainable parameters, you update all of them for a specific task. Okay, so in this case, what we do is we bring in a new small subset of parameters and we train that, okay, or we fine tune that, thereby reducing the memory and computational efficiency. So it also, right, there is this basic understanding here, like it builds on the understanding that large language models inherently possess low dimensional structure. So just to give an analogy, right, if you see in PCA, principal component analysis, we try to we have higher dimension data, we try to reduce it to smaller dimension data by performing PCA. Okay, we are while we are doing that, we are trying to retain as much information as possible, okay, such that the model is able to capture the nitty-gritty details of the data. Okay, so that's what here it refers to. Okay, the large models possess a low dimensional structure. Yeah, so we are trying to capture that low dimensional structure from a large large model. Okay, so LoRa uses low rank matrices to capture the core concept. Okay, so that's, as I said, in PCA as well, we try to have a large dimensional data, we are trying to capture it into lower dimensional data. Similarly, LoRa does the same, at least conceptually. Okay, that's what is happening here also. So consider, right, you have a model which is like GPT or Llama 3 model. Okay, there is weight update is happening and you have an X matrix. So what you do is you split it into or decompose that matrix into two. One is W, which is your pre-trained weights, and there is A and B matrix, which is the low rank matrix that you are building. Okay, so here W is the pre-trained matrix or weights, and A and B are the low rank matrix that gets updated during the fine tuning or training process. So basically to understand that, right, how it is updating. So basically when you're doing fine tuning job, right, you will be having something called as delta W, which is here. Okay, decomposition delta W, right? This is what is weight update that is happening during fine tuning job. So in a actual fine tuning job, what you do is you will be updating W plus delta W. That's what is happening for the whole all the weights of your model, right? That's what is happening. In this case, what we'll have is delta W is nothing but your A and B, okay, which is the low rank matrix. So in LoRa fine tuning, instead of updating W, what we do is we decompose delta W using A and B. So if you see in the diagram here, okay, delta W dot X. So this is the part that weight update is happening, is what we are trying to fine tune. Okay, so here if you see, this is again the same part, the intrinsic rank hypothesis. The significant changes in neural network can be captured by low dimensional representation, which is again I'm going back to the PCA to understand this basic concept. So what is A and B, right? So as I showed in the previous slide, there is delta W which needs to be updated. So the delta W is nothing but A and B, which is your low rank matrix. And the way the weight update will happen is, so you will be these are like two, you can consider it as two layers, okay, which will be getting updated, okay, and of dimension D comma R and R comma D. Now in this equation, W is what the pre-trained weight, and this is getting DW, which is not DW, delta W, okay, which is fine-tuned weights or low rank matrices, and this will overall give you the weight update at the end. So to understand here one more thing, right, the impact of low rank on trainable parameters, right? So here if you see, W is D cross D, the dimension is D cross D, and if when you are trying to do fine tuning job without LoRa, you have to update D square parameters, okay. But when you are doing it with the low rank matrices like B and A of sizes D comma R, D into R, R into D, okay, so you are trying to update only 2 times 2 DR parameters, where R is very less than D, okay. So we have reduced it from D square to 2 DR, where R is very small compared to D, okay. So that is the major change, or in terms of number of trainable parameters, that is happening, which will reduce the overall training cost, the memory efficiency that comes in, and the loading and the sharing of the models, right? Those all things comes into picture. So at the end, right, let's understand what it benefits, right? So the memory footprint, right, when you're training the model, it is very less, and the training will be quite faster, and you can use very small GPUs to load that specific smaller low rank matrix or model, right? You want to call it model, you can call it model, yeah. And you can also scale it to larger models. It is that irrespective of the models, right, you can build your LoRa, like a low rank adaptation for a specific model, okay. So these are the techniques, okay. So we are at the end of the LoRa video. So these are the references that we have used, and I'll be mentioning them in the description. So let me just go back and review what we have seen. So at the end, what we are doing is, so we are just trying to fine tune a model, okay. Compared to your large language model, we are trying to capture those information into a small number of weights by fine tuning it on specific data set, which will instead of doing it for all the weights of a large language model, we are just creating a smaller model side by side and using that for a specific task, okay. So yeah, with that I'll be concluding this video. Thank you for watching.